Let us angle the picture with the two-sphere S2 in the ordinary and familiar three-dimensional space. Geometrically, S2 is the set of all points exactly one unit distance from a fixed point that is called its center, a perfectly symmetric surface with no preferred direction. Let us now place the center of the sphere at the origin of a Cartesian coordinate system. In this coordinate system, the sphere S2 is a set of all points x, y, z in R3 satisfying x squared plus y squared plus z squared equals to 1, which expresses in an equation that the Euclidean distance of a point xyz lying on the surface of the sphere from the origin of this coordinate system is 1. Let us pick a point on a sphere. The red line from the origin to that point has unit lengths. The disadvantage in this description is that we specify 3 parameters subjected to constraint in order to describe something that is inherently two-dimensional and should in principle require only 2 parameters. Let us introduce a parameterization for the surface of a sphere where exactly 2 parameters are used to describe the two-dimensional surface, in which the constraint of the unit distance from the origin is satisfied automatically. The coordinates we will introduce are called the spherical coordinates. The angle theta is the angle between the radius vector and the positive direction of the chosen z-axis. At the north pole, theta equals to 0. At the south pole, theta equals pi radians. Let us now project the radius vector onto the z-axis and onto the xy plane. The length of the projection onto the xy plane is sine theta. We will denote a second angle by the Greek letter phi, as the angle in the xy plane measured from the positive direction of the x-axis to this projection. Now we can compute the remaining components. X equals sine of theta cosine of phi. Y equals the sine of theta sine of phi. And finally z equals cosine of theta. Just as promised, in those coordinates, the unit distance constraint from the origin is satisfied automatically. Plugging in the parameterization of those coordinates, we obtain x squared plus y squared plus z squared equals sine of theta cosine of phi all of it squared plus sine of theta sine of phi all of it squared plus cosine of theta squared. Factoring out sine squared of theta, we get cosine squared of phi plus sine squared of phi in the brackets, which is 1. So what remains is sine squared of theta plus cosine squared of theta, which also equals to 1. This proves that the constraint is indeed satisfied, and any point in this parameterization indeed lies on a unit sphere. We state a varying from 0 to pi, and phi in the half-open interval from 0 up to 2 pi not included. These formulas sweep out the entire sphere. Limiting theta to be in the 0 to pi interval ensures a unique parameterization of each point except the poles. If we fix theta and vary phi, we trace a latitude, a horizontal circle parallel to the equator. Each latitude is the set of all points on the sphere at a constant height, where z equals cosine of theta. If we fix phi and let theta vary from 0 to pi, we trace longitude curves, half circles on the sphere connecting pole to pole. Stepping phi around builds a family of meridians, like time zones on a globe. Longitudes intersect every latitude exactly once, except at the poles, where all longitudes meet. Together, longitudes and latitudes constitute a coordinate grid on the sphere S2, 2 angles, 1 unit radius, and every point accounted for. This 2-angle picture is a template we'll echo in higher dimensions. Keep theta and phi in mind. They are the keys to navigating spheres. Now let us examine the general case of a point not on the unit sphere. A point xyz in R3 always lies on the surface of some sphere. If its distance from the origin is r, it lies on a sphere of radius r. The Euclidean distance r in this coordinate system can be computed from the Pythagoras theorem as r equals the square root of x squared plus y squared plus z squared. With these angles, the Cartesian components scale exactly as in the case of the unit sphere. They're simply getting multiplied by r. So we have x equals r sine of theta cosine of phi, y equals r sine of theta sine of phi, and finally z equals r cosine of theta. We have already computed the transformation from the spherical coordinates to the Euclidean ones. If someone would specify r, theta, and phi, we have derived the formulas to computing the Cartesian coordinates x, y, z. Now, let us compute the inverse map from the Cartesian to the spherical coordinates. We already have the formula for the radius r, which is the square root of x squared plus y squared plus z squared. By definition, cosine of theta equals z over r. Figuring out the value of theta is straightforward, as z over r lies between -1 and 1, exactly where the inverse of the cosine function is well defined, as the cosine function maps the interval from 0 to pi onto the interval from -1 to 1 in a bijective correspondence, and its main branch would yield the expected result between 0 and pi. Since the cosine function is 2 pi periodic, adding an integer multiple of 2 pi to any value of the arccosine function yields an equally valid choice of an angle. To avoid this ambiguity, the main branch of the arccosine function is chosen to be the one that yields the result in the 0 and pi interval. The construction of phi is more tricky. To prevent phi from completing a full revolution, we exclude the value 2 pi from its range. Naively, we could say that phi equals the arctangents of y over x, but the tangent function is pi periodic and has essential discontinuities at odd multiples of pi half. The main branch of the arctangent function returns the values between minus pi half and pi half, and it loses quadrant information. In order to restore the correct quadrant and force phi to be between 0 and 2 pi, we add constants that exploit the pi periodicity of the tangent function. In the first quadrant, we set phi to be the arctangents of y over x, which yields values in the half-open interval from 0 to pi half. On the positive y-axis, as expected, y over x is not defined. Nevertheless, we can set phi to be pi half, as the limits of the tangent function, as the argument tends to positive infinity, exists and equals to pi half. In the second and third quadrant, where x is negative and y is arbitrary, we add pi to move the angle into pi half 3/2 pi interval and extend the first quadrant definition by setting phi to be equal the arctangents of y over x plus pi. Similarly, on the negative y-axis, we set phi to be 3 pi over 2. In the fourth quadrant, arctangents of y over x yields a result between minus pi half and 0. So we set phi to be the arctangents of y over x plus 2 pi to place it in the open interval 3/2 pi to 2 pi. At the origin, phi is inherently undefined. With this construction, phi is single value in the half-open interval from 0 to 2 pi. And it is defined at every point except the origin. There remains an unavoidable jump discontinuity along the positive x-axis, as approaching this ray from above gives an angle near 0, while approaching it from below gives an angle near 2 pi. This jump is inherent, and any single value choice of the angle on the function plane must have a branch cut somewhere. I wanted this video to be more than just an animation. One of the links in the description will take you to this Desmos interactive environment where I created the exact clone of everything that you've seen in the animation. I even preserved the color scheme of everything that you've seen. The usage is supposed to be very straightforward and intuitive, but nevertheless, let me just give you a quick walkthrough on how to use it. If those checkboxes are unchecked, check them. This box will enable this dark mode visualization where the color scheme is preserved, and you need this checkbox to see what's happening inside the sphere. Clicking here, Desmos will plot the surface of the sphere, which is the collection of all points in this coordinate system whose distance from the origin is constant and equals to r. Clicking here, Desmos will draw a point on the surface of the sphere which is parameterized in the spherical coordinates as we've seen previously. The only difference is this one subscript that we need due to technical reasons. The Desmos does not fully support, as of now, of Greek letters. So in order to create those sliders, we needed this workaround with the one subscript. Clicking here, Desmos will draw the radius vector. So it's very nice for readability. It's a folder, but if you click the folder, you'll see that the only element of this folder is the straight line equation, the equation of the line that connects a point on the surface of the sphere to the origin of the coordinate system. We can also have the dashed line projections that we've seen on the axis. As of now, Desmos does not support in 3D mode dashed lines. So I created a dashed line by an aggregate of short segments, whose equations you can see here, and aggregating them together creates this effect of a dashed line. You can dive deeper afterwards. We can also draw the projection components on each axis. Clicking here will draw all of them simultaneously. To see better what's going on inside, if we want, we can undraw the sphere. And later I will show you another method to see inside the sphere. But as of now, you can just click the sphere and undraw it. If you want to see the angle arcs, by clicking here, we would have a phi arc and theta arc. Basically, each arc is just an equation in the corresponding plane of the circular arc equation that corresponds to the angle that is determined by the value of the sliders. The angles are, of course, always only in radians in this visualization and in this video and in my videos in general. Radians is the only unit of angles I would ever use. If you want to see the labels, it's a bit more tricky because Desmos in 3D mode does not support, as of now, labels. But if you want, you can see the label. I created the label of phi by just inserting into Desmos a set of parametric equations that combines an equation of a circle and of a straight line. If you're curious as to how those equations are determined, you can click the phi label folder and see the exact definition of those equations. Similarly for theta, the later theta was created as a collection of parametric equations. Going here to the theta label folder and clicking it will draw theta. Basically, theta was created as an equation of ellipse and a segment of the sine function that was drawn. So in this way, we can create the labels. But for now, let's undraw the labels. Also, we can see that by tweaking or adjusting those angle parameters, everything adjusts correspondingly. We can now, if we wish, we can draw back the surface of the sphere. Let me zoom out. Okay, so what else? So we've seen the labels. Another thing that we can see, and was in the animation, is the longitudes and the latitudes. So for that, let's undraw everything else, just for the beauty of it. And let's undraw the dashed line projections. We're not going to be needing them anymore. And let's undraw the point, and the sphere itself, and the arcs. Okay. So going into this folder of latitudes, clicking here, I'll show you what's inside. Basically, it's the list of those parametric equations of lines. The value of n, by adjusting it, you can decide the number of latitudes. So clicking here, you would see there's only one latitude, which is the equator. By adjusting n, you can have as many latitudes as you want. Well, not as many as you want, because any Desmos list supports, as of now, up to 10,000 elements. But, you know, you can increase this to 100 value to even more. Similarly, we could have the equations for the longitudes. If we undraw those, going here, it's the same principle of parametric equations and a set of parametric equations. So by adjusting the parameter k, we can decide how many longitudes we're going to have in this visualization. And we can create the grid that we've seen in the animation. Basically, we can vary the density of the grid any way that we like. So it's, you know, nice to play and adjust it. Finally, if you want to see inside the sphere but not fully drawing it, there is a nice way to use the parametric equation for the surface of the sphere. So if you were to go to the surface of a warped sphere, here we have the equation of the sphere in spherical coordinates. So clicking here, we'd have the same surface for the sphere. Now let's draw all the components that we had. So we had the radius vector, we had this point on the surface of the sphere, we had the dashed line projections, and we had these projections on the components. And let's even draw back the phi arc and the theta arc. Okay. So if we want, and even theta label and phi label. If we want to see what's going on inside the surface of the sphere, we can now open it up in many possible ways. So by adjusting this parameter s, we can open it up like this. We can maybe bring it to here, and then we can also adjust this parameter. So we can open up like this. Another way to open up the sphere is through those parameters that correspond to theta. So we can open up the sphere like this and see what's inside. Or if we wish, we can open it up from the bottom and see what's going on inside the sphere. Or any combination of those, it's really up to you to interact with this visualization and open it up whichever way you like. There's countless possibilities to explore here. So let's undraw then warp sphere. And one more thing that I wanted to show you is those family of lines that you've seen in the animation as well. So let's undraw those. Those lines are on the surface of the sphere, where we preserve the radius as a constant. So now let's undraw the phi arc and the phi label and theta arc and theta label. And let's just draw the sphere. So finally, we arrive at this equation for a single curve. This is the equation of the curve that we've seen in the animation, where the radius vector was traveling and tracing this beautiful curve. Basically here you have two parameters. If we go here, we have parameters alpha and beta. Basically, alpha is just the rate of change of, here this is the angle, this is angle theta. So by tweaking it like this, changes slowly, or yeah, it's less dense or more dense. Note that this value here is pi over alpha. So we can play with the density of this curve by adjusting this parameter. Also, this parameter beta is the initial rotation of this curve. So by clicking beta, we can have this nice animation of this curve rotating, right? And on the fly, we can adjust this density. Finally, one more thing I wanted to show is that we can create a family of those curves. So now it starts with one curve, but then we can increase the density of those curves, and then Desmos will draw more curves in different colors. You can click the colors folder to see exactly how the colors are encoded. So by increasing the number of number L, you can increase the number of curves and their density. What you see here is a nice mathematical structure called affiliation. Well, except at the poles, but the basic idea is that, at least locally, those curves never interact and then they fill the surface of the sphere. It's also reminiscent of the structure in mathematics that is called vibration, but maybe more about this later. And you can create those beautiful color patterns that you see. So countless possibilities to explore here. So if this reminds you of something that you've seen about Brilliant.org, well, this is no coincidence. I think their method of teaching is brilliant, and it inspired me to make this interactive visualization with Desmos for you. I'd like to take this opportunity to thank Brilliant.org for sponsoring this video. Brilliant encompasses a large variety of courses at various levels in mathematics, physics, engineering, AI, and even quantum computing. There is something for everyone on Brilliant.org. You can find the link in the description with a 20% discount to Brilliant.org. Don't stop your learning as this video comes to an end. Continue with Brilliant.org. As the greatest investor of all time, Warren Buffett once said, "By far, the best investment you can make is investment in yourself. So what are you waiting for? Scan the barcode on the screen and invest in your personal development."